Very good. Also, in the spirit of the holiday, though, I'm going to lie to you, or put more charitably, I'm going to try to trick you. If someone can the tricks that come in the presentation, you get to pick the type of candy. And if you wait until Friday, that'll probably all be at desserts anyway. Okay, I think everyone knows me, but in case anyone's on Zoom, my name is Essick. I'm an assistant faculty here. I'm going to be talking about this paper, which is in press with PRD. It's a little bit of a rebuttal to this paper, which was published in PRL 4 years ago. And in particular, what types of events carry a lot of information in catalogs. So if you're interested in constraining like physical underlying things about the universe, and you're doing this with a catalog of detections, there are natural questions that arise. Like, do you just need to wait for the one golden event that's going to tell you everything about the universe because it's going to be so beautiful and clean and loud? Or should you process as many events as you have, just try to, just throw as much compute at it? And actually, what we're going to go to towards the end of the talk is, can you actually think through what is the most cost-efficient way to do that? And is there some sort of natural optimization problem that presents itself? Hint, there is. Okay, so focusing on gravitational wave signals from compact binary coalescences, because this is my bread and butter. But a lot of these things, like this type of approach, should apply to other catalogs. The scaling may be a little bit different, and therefore some of the conclusions may be different. But I'm focusing on CBCs as observed through gravitational waves. I'm also going to be focusing on the Fisher information matrix, which is kind of like an old-hand way of calculating things quickly in gravitational wave literature. It is a much more general technique, though, and applies to basically any problem you have. And so the Fisher information matrix for parameters I and j, okay, this is formally defined as an integral over your data parameters. And so I should write this up here. Data is x, params are theta. And so this is a vector, and the indices that I'm writing here are the parameters of this vector. So the indices of this vector. So this thing is defined as an integral over data space d by d theta I log p of x theta times d by d theta j log p of x of theta. And so you can also integrate by parts, and people will sometimes write these as two derivatives of log theta, log p, things like that. But this is a common definition of it. And so you might ask, where does this come from? Come on, man. And so there are many different ways you can actually motivate this. What this looks like through something called the Kramer-Rao bound is this is greater than or equal to the covariance matrix inverse. So I would call this a precision matrix. This is a covariance matrix, which means how well I can constrain individual parameters, theta I and theta j. And it's related to this Fisher information matrix. So if I can constrain something really well, that means my covariance will be pretty small, like especially along the diagonal, will really small. That means that I would expect the Fisher information matrix to be really big. So big gamma implies small c, which means I can constrain things well.
I guess you have to pick a norm for doing this comparison as well. Like you're saying less than or equal to. Like...
So what I mean is that like specifically with the less than or equal to, the diagonal components of this are less than or are greater than or equal to the diagonal components of the inverse of this. That's what I mean. That's what's called the Kramer-Rao bound, which shows it. Okay. And so this is kind of a beast of an expression for the typical model for how our noise or how our data is generated in gravitational waves. We assume it's stationary and Gaussian. What that means is that p of x given theta typically looks like e to the minus 1/2 x minus mu I ij inverse j. So some multivariate Gaussian. And here I'm using sigma, capital sigma, to mean the covariance matrix of this multivariate Gaussian. Okay, great. And so this is a fancy way of writing stationary Gaussian noise. The Gaussian part is obvious. The stationarity actually comes in assumptions about this, the form that the sigma can take. And so as it turns out, if you plug this into this expression, what you get is d theta I log p is going to be d theta I minus 1/2 x minus mu inverse x minus mu. This is equal to x minus mu I j inverse d mu j d theta. I'm going to change this to alpha so I don't confuse myself. Everyone following me? I just took a derivative and I get one factor from this, one factor from this. So that is what kills the two. And then I know that this is symmetric, so I can interchange indexes and then combine them. So this is equal to this. If I then plug this into these two places, what I get is that gamma ij is equal to the integral dx p of x given theta times x minus mu I x minus mu k, and then I have ij inverse mu j theta alpha kl mu l d theta theta alpha theta. Okay, taking a step back, what have I done? I took this expression, I plugged it in here and here, and then I've redistributed. So I took these factors, the x minus mu's, and I lumped them together. And then I took the sigma inverse partial of mu's, put them over here. And so there's this goes with this guy, this goes with this guy, and the d by theta alpha and theta beta corresponds to my two indices over here. Okay. Cool. None of this stuff depends on x. Doesn't actually depend on the data. Just depends on the mean of my model and the covariance, which I'm assuming is fixed. Okay, great. So this integral, I'm just doing this. And this expanded looks like xi xk minus xi mu k minus mu I xk plus mu I mu k integral dx p of x and theta. Okay. I can recognize that doing this, right? This is just a Gaussian distribution. And so I can write this down. Well, actually, I can look at this. That's how I did in my notes this morning. But this integrated against the Gaussian, this is just a definition of the covariance matrix, right? And so, it's the eraser, you fool. So this whole bit here looks like sigma ik. That's the definition. And then over here, I have a sigma ij inverse, sigma kl inverse, d mu j, d mu l. Okay, that and that become a delta kj. And so what I get is my gamma alpha beta is a very appealing expression, JL. And I have the derivative of the mean with respect to this parameter. So this is like the change of my model, inverse of my noise matrix, derivative of my model with respect to the other parameter. And this, so this is a, if this is a very straightforward covariance matrix, which it is for station Gaussian noise, in fact, this is diagonal. and these things are readily computable, which they are for many of our models, then you can just plug this in, you can compute all the matrix elements you want of this, invert, and this is like, people have been doing this since the early 90s, if not way before then. I mean, like Fisher was doing this in the 20s and the 30s. So I'm not telling you anything brand spanking new. Okay. So, yeah. Mu is the mean of this process for your data X.
Okay.
So in this notation, mu would be like your waveform model.
Oh, that.
Yeah. Okay. And so what this ends up looking like for Gauss or gravitational waves is more often expressed this way. dh alpha dh theta for the experts in the room. And there's usually a star here. And so in this, h is my signal model. Theta is still my parameters. This is my power spectral density, one-sided power spectral density, and I integrate it over frequencies. That integral is just the sum. This is a diagonal matrix. So it's a one-dimensional sum. That's what an integral looks like. Anyway. All right. I promise there will be somewhat fewer equations moving forward. But this is the basic idea. Fisher information matrix, which is defined this way. Why do we care about it? It's an approximation for the inverse of the covariance matrix, so how well I can constrain things. And I can actually compute it pretty reasonably given some signal model. So this is a workhorse for usually forecasting estimates, things people do like that. Okay. Any questions? All right. Yeah.
So you're fitting radial velocities.
Yep.
So parameter theta would be masses.
Yep.
So functions of theta
that represent the RV, the predicted RV curve. Yep. X is the data that you actually record, and then if you assume that then each one of these things, this would be a diagonal matrix with independent covariances for each radial velocity measurement.
Hi, we've lost your audio.
For example, Fisher called this matrix the information, but it's not the Shannon information. It's different. So like many different people will throw around the word information. So if you're reading in literature, just be careful. That word may not mean what you think it means for that. So I'm going to use a particular definition of information, which I'm going to call I, for hopefully obvious reasons. And I'm going to claim that this is a useful thing. Why do I think this is good? So what I mean is that the determinant of this matrix, so the Fisher information matrix, is what I'm going to use to quantify the information. Why is this a useful thing? Well, this I told you is a proxy for the inverse covariance matrix, right? And now the determinant of the inverse covariance matrix, if I diagonalize this matrix, right, put it into its eigenbasis or whatever, then I'm just sort of taking the product of the diagonal, right? So this would look like the product of I to little m, number of dimensions in this matrix, of the eigenvalue I, right? But I'm going to write this as sigma squared I inverse in that basis, right? So this is the inverse covariance matrix, right? And actually, I can just do this. That's how determinants work. If I do this. So if I look at this, this is in an eigenbasis. So this is in I basis. Each one of these things looks like it has some dimensionality, right? It's in some direction, the uncertainty in that direction. I'm multiplying all those together. So this looks like the volume that is allowed a posteriori, some high dimensional hypervolume. So if it's a two-dimensional space, it's actually an area. If it's three-dimensional volume. If it's more than that, it's some. That would be all the sigmas multiplied together, and then I have effectively -2. So what this means is that this thing, this I, should roughly go like the inverse of the volume that is allowed by my measure. And so if I have a big I, what it means is that the volume that I'm constraining these parameters to possibly be, it must be really tiny, right? And so what does it mean when I constrain something really tiny? Well, in English, I might say that is carrying a lot of information about those parameters. There's very few parameters that are actually compatible with quantification. So this is my definition of information, which as far as I know, was introduced in this context in this other paper, the one that was published before me. So I'm piggybacking on this.
So we have a question from Zoom.
Yeah.
And the question is there a partial analogy to the differential geometry approach for finding the optimal number of templates?
Yes. Yes. So oftentimes my interpretation of this question is if you were building a template bank to run for searches, like you're trying to filter a lot of data and say like, wait, was there a signal somewhere in this parameter space? There's a natural question of where you put those templates, right? And this Fisher information matrix will tell you basically the ellipsoid, the uncertainty ellipsoid in that whatever dimensionality space you have. And so if you have a bunch of ellipsoids that look like this, in this direction, you better put a lot of templates. In this direction, you don't need as many templates. And so people use the Fisher information to try to design optimal template placements, because if I have one template here and one template here, I should be able to tell those really apart. But if I have a template here and a template here, I can't tell those apart. So I'm kind of wasting compute. So that is the image. That being said, for modern template banks, people actually place them stochastically, because it turns out the algorithms don't do that much better than just random template placement in many places. All right. Good.
Yes. CITA diagonal.
This?
Yeah,
This, in general, this will not be diagonal.
okay.
So over here, if I take this thing, this CITA, which is not diagonal, but I compute the determinant of it, that is equal to the product of the eigenvalues, because I can rotate into the eigenbasis with
Oh, I see.
unitary operators.
So on this side, you have a CITA inverse is less than or equal to the Fisher information.
Yes.
How often is it that it's close enough of the actual Fisher information?
So this equality happens. So this is a better approximation when the SNR, the signal noise ratio, is really, really big. So basically for louder signals where the actual signal is bigger compared to noise, you get, this is a better and better approximation. It depends on your problem a little bit, like how big is an SNR. But I'll get to that a little bit later, but the typical numbers for gravitational waves would be like SNR probably around 20 or 30 before you would really start to believe that maybe this is not complete graph, this approximation. But definitely in the very high SNR limit, you would expect this to hold. By that I mean over 100. So if you had a golden event, something that was really loud, where it's like you get a lot of information about parameters. This is probably a few. Okay, so this is my definition of information. So now, if I want to ask the question, where does the information come in my catalog events, right? Or what is the overall constraining power, or information, I should say, carry my events? What should I do? Well, let's see what happens if I add up the total amount of information. So I'm going to call I sigma depth. And what do I mean by this? Well, I'm going to sum over events E to N, where the information of individual E. So I'm just going to add up all the information. And so the last thing that, well, if I have many events, right, this can also be written as N times a D and SNR. I use rho in the literature. D rho on some distribution of rho of the individual information that depends on rho. And so typically you take this from some rho threshold, infinity. The signal noise ratio has to be above some value for you to constantly detect it, but it can be as high as it. And so there's some distribution here that you're basically sampling from when you observe this catalog, when you collect a lot of things, it's an overall number that you have. And so this is I'm claiming it as quantity. The last thing I need to tell you is that for many of the parameters that we're interested in, there is a special scaling. Like, this is great, but I wrote down this thing here, and I haven't specified what it is. So this integral expression is not particularly helpful. But it turns out for several different parameters, in particular, if you have a signal model H that looks like some amplitude, e to the I psi of parameters, your parameters only or primarily affect the phase of your signal. What this means is that d alpha of H is going to be I d psi theta alpha a e to the well. Right, so I'm just picking up the phase, the change in the phase. When I plug that in here, what this means is that I would have 2 integral f of H star, and then I will have a plus I and a minus I because it's a complex conjugate. So I would have d psi theta alpha, d psi theta. So going for, this is a general definition. I assume stationary multivariate Gaussian. It gets me down here with the variables that are common in the gravitational literature. That gets me here. I then assume that my signal actually depends on these parameters in this particular way. That gets me here. And the last thing is that I can rewrite this in a sort of stupid way, but it ends up being nice as rho squared times df h squared over s, the alpha psi theta psi over the f h squared over s. There's two, whatever the factor was here. And this is because the definition of the SNR is this thing down here, forward station and gravitational noise. That's how it's defined. And so the signal noise ratio that we talk about in gravitational waves depends on the signal amplitude in this particular way. Why is this a useful thing to do? Well, if I look at this, it no longer depends on the overall amplitude of the signal because it's going to cancel out between the numerator and denominator. So I've got something that won't scale with the amplitude of the signal times the expected scaling with the amplitude of the signal. So this is like I've sort of broken the problem into separate parts. What does that mean? Well, it means that this gamma, which gets fed into this I, right, is going to have a particular scaling with rho, times something that doesn't depend strongly on rho. So what does that look like? If my gamma looks like rho squared times gamma hat ik, so this thing doesn't have any strong dependence on the SNR. I've just pulled all that stuff here. Now I take the determinant of this, right? If this is a d-dimensional matrix, right, this looks like rho, the 2D, gamma hat. Everyone understand that manipulation? Okay, so this is just every matrix element carries this thing. So if I'm taking the determinant, it's like I'm taking the product of the diagonal. So I will have d factors of rho squared or overall coefficient of rho times something that I'm going to claim design. The other piece of information I need is that p of rho tends to go like rho to the -4. Okay. And so the reason for this is that rho for gravitational wave goes like 1 over the distance, the velocity distance. Okay. And if my systems are uniformly distributed in distance, then p of p goes like dl squared, where d has to be at least close enough for me to detect it. And then if I do a change of coordinates from this distribution implies this distribution. Because I get two factors of this, and then I also have a Jacobian from dl to d rho, and so like d rho, looks like d squared. So I have two factors of rho from this, and then two factors from this Jacobian. So, okay, great. I have this. I now have an expression that I can plug in for each individual events. This would be IE. I have this distribution over rows, right? Let's plug it in. Let's see what we get. And so I will get something that looks like n d rho from rho threshold, rho to the -4 times something that looks like rho to the 2d, and a determinant of something that I'm going to say does not depend strongly on rho. Let's factor that side. This looks like n get gamma hat, and then this integral, right? D is an integer, okay? So I never will actually have the case where rho is -1, so I'm not going to worry about logs. So this will end up looking like 2d -3, and then rho max to the 2d -3 minus rho min to the 2d -3 of the threshold, and I've introduced a maximum here. Voila, I remembered my count 2, and I did a power law. Great. Excellent. So now I have something that tells me about the overall information. Let's examine this object. Okay, what if I'm asking a question about a single variable? So d is 1. 2d is 2, -3 is -1. So I'll go over here. when D is equal to 1, I sigma det is equal to, or goes like some prefactor, rho threshold to -1, rho threshold rho max -1. So if rho max goes to infinity, like the thing can be as loud as it wants, this goes to 0. Great. Now let's see what happens when D equals 2. Okay. When D equals 2, 2D minus 3 is 1. And so this goes like rho max minus rho min, or rho threshold. Now what happens when I take this to an infinite? It's like infinite upper limit. Well, that goes to infinity. So this whole thing goes to infinity. So it says that I have an infinite amount of information I can. And so to say this again, if I ask a question about one variable, I have a bounded amount of information. If I ask information about 2 or more variables simultaneously, it seems that I have an infinite amount of information I can. And in particular, the more variables that I include, the more this divergence happens, right? The stronger it depends on the loudest thing that you've ever seen. So this suggests that these golden events that happen, that drive it, right? So let me give you an example. Let's say I'm worried about the radius of a neutron star. That's like all neutron stars roughly the same radius, so that's one variable. And then I'm worrying about, the other variable I worry about at the time of the event is whether or not James cut his hair that day, right? Does the radius of a neutron star have anything to do with whether James cut his hair that day? Probably not, right? Sorry, James, that's like in my eye line, so that's why it's your hair. So what that would mean is that this should be diagonal. Like those things should not be correlated at all, right? And in fact, I can ask a bunch of questions about other things, whether Sam forgot to tie his shoes, whether the Reed broke the idea lab yet again. That was probably always true. But so you can ask a bunch of uncorrelated questions and make this matrix have as high dimension as you want, right? And so what this analysis tells you is that if you ask questions about completely uncorrelated things, it will change the scaling of whether or not you're able to answer an actual astrophysical question. So, yeah.
I epsilon that again. Like the primary.
This,
Yeah.
sigma det. So this is, I'm saying that this is a way to sum up all the information
From all the
from everything in the
catalog.
catalog. Yeah. Okay. So no one got it. No one gets candy. It's actually trick 2. You guys missed trick 1 entirely. Trick 2. This is wrong. This is not correct. Cross it out in your notes. And so the absurdity of this statement sort of shows that. Like if I ask uncorrelated questions, it seems to affect my ability to get information about individual systems or individual parameters. And in particular, if you look at this scaling here, and then you ask questions like, well, what would the typical uncertainty be in an individual dimension? Then maybe what you would care about is something that looks like I sigma det the 1 over d. It's going to be like your typical uncertainty in any individual dimension. And what you can see is that this thing, if I take that to 1 over d, that will still depend on d, right? And so the uncertainty in any individual direction will depend on whether or not you ask other questions at the same time. Now, from first principle, that's not an absurd thing. Like we were talking about before, if I pretend that I know the inclination of the system perfectly, that will affect my ability to constrain the masses. And so there are real degeneracies there about what parameters you include, which ones you don't. But this thing, where I can just ask a completely unrelated question, and then it affects my ability to constrain something, that smells wrong. And so this approach is what was adopted in this paper, published in PRL, which is a more prestigious journal than would accept my paper, but it's fundamentally. So, Reed, you just wasted a bunch of our time. What is the correct thing to do? Well, everything up until here, I'm gonna keep that. Until this, where I claim that this is an interesting thing. This is the faulty assumptions. This is not how information sums between events in this picture. What is the correct thing to do? Well, this is also a cautionary tale when people throw words like information theory at you. Like, you gotta sort of make sure that it's not just buzzwords that are being combined, which can happen a lot when people think. So you want to have make sure you understand what is the basic principle. So I argued that this was an interesting measure of the information because it was related to the volume that was allowed, the volume in this primary space that was allowed. Okay? So if I want to know the total information in the catalog, by that logic, I should look at the total volume that is allowed after form. Okay. And what does that look like? Well, if I have n different events, and each of them I can compute this information matrix is more approximate. And it turns out for loud events, like we were talking about before, I can approximate the likelihood of this thing as a Gaussian with this precision matrix. This so for a loud signal, P of x theta, we can approximate it as -1/2 theta minus some theta bar, okay, or some Gaussian with precision matrix or inverse covariance matrix given by the Fisher. I'm not going to justify this too much, but it is a common approximation. Sometimes goes by the name of a loss approximation.
Shouldn't that be theta given x?
No. What I mean by this is it is a distribution over the data that I observed. Like that is a function of the parameters, right? And so this thing depends on the data. I take your point. It is a weird way to write it down, but this is the approximation that people typically write. It's something like this, and then if they wanted to do theta given x, they put some prior over here. And typically it'll take an exponential prior and then. Fine. I want to talk about likelihoods right now. So if this is for a loud signal, this is an likelihood, right? And my observations are independent, noise is dependent. Then the joint distribution or joint likelihood is just the product of these. So P of a whole set of observations given some set of parameters. Is then E to N theta minus theta bar E gamma E theta minus theta bar. So I've just multiplied a bunch of these strings of events, and you can do the algebra, simplify this because the product of the exponentials is just the sum of the exponentials. This is going to look like E to the -1/2 theta minus something. So I'll call it theta tilde. Sum gamma E to N theta minus theta tilde, and then possibly some other factor here that doesn't depend on theta. And so you can see that just because I'm going to have a theta squared term for each one of these contributions. But if I add them all up, I will get a theta squared term as the sum. So this means that in this analysis, the total precision matrix should be the sum of the individual precision matrix because of this multiplying out. Great. Now, if I want a measure of the information, like I was saying up there, I'm going to call this one det sigma. I should take the determinant of this total precision, because that's going to be the measure of the volume left when I constrain everything together. And so this I could write as determinant of n integral d rho give rho ij function of and then I get something. But notice that here, I sum first, and then I take the determinant. And before, I took the determinant and then I summed. And this is the key difference. So if I take this scaling, where this thing goes like rho squared, and the rho to minus 4 scaling here, right, plug that in, I will then get something that goes like determinant of n rho small gamma hat ij integral d rho to minus 4 rho squared. So this integral I can do. This goes like rho threshold minus 1 minus rho max minus 1. That's what we did with the d equals 1 case. Very simple, equal to 2. Now if I take this to infinity, that goes to 0. Okay. And so I just have a threshold here. I have this thing, but the n and this threshold don't depend on the dimensionality. They happen for every matrix component that's the same. So I can take them outside of that and write this as n 1 over rho threshold. And this whole thing goes to the d, which is the rank of the matrix, times the determinant of gamma hat. Okay, now let's play our game again. What if d is 1? What if d is 2, right? Then d is really only affecting this. And d is d, it's only affecting this. And in particular, if I take this thing, that I said before with a good indicator of whether or not this dimensionality is less than things, this goes like n rho threshold times some determinant of some nasty matrix 1 over d. So this thing is d-dimensional. So you might expect it to scale with d. And so this, now if I ask a question about one individual thing, the overall scaling is not changing, it's not depending. All right. So other trick. This only works if these theta that I'm talking about are shared between events. Right? If it's the same parameter for each event. So if you have a bunch of neutron stars that all have the same radius, that works. But if you have a bunch of black holes and they have different masses, there's a different parameters for each different events. So this is a subset of possible measurements you can do. The other thing that is not accounting for is selection effects. Some of the population, like there are a bunch of things that actually need more complicated analysis. Think that you can write more. But if you make these assumptions in this simple like stacking Fisher, multiplying Fisher approximation, you should get all the way to here. And so what does this say? This says that the important events, the things that are driving the overall information in the catalog, are the things that live right by rho threshold, right? Like this doesn't depend on the maximum, like the loudest thing I saw at all. It depends on the quietest thing I saw. And why is that? It's actually because of this, which is this. Off we go. Try to not put this to that. Yes.
So just trying to understand that. So then is the fact that we did a likelihood what takes care of like if we precisely measure whether James got a haircut today, but it doesn't, there's no physical connection between that and what we're measuring, so the likelihood will take care of that if that has 0 noise.
So sort of in this picture, some precision matrix, right? And so let's say this is a 2-dimensional thing and it's the radius of a neutron star and whether James got a haircut, right? Radius of neutron star, James got a haircut, right? If this is block diagonal, right?
Yeah.
Then any information about this doesn't talk to this, right? And so it's this, the fact that it's completely uncorrelated, that is separating it out. But okay, so let's say we don't worry about this stuff. But here, let's say it's the greatest of any transfer, the maximum transfer, like other things that are shared up, like some deviation parameter from PR, like what is big P, something like that, right? That could all live in here. It could generally be some complicated correlated thing that shows up in this. And so if you have strong correlations, like it can affect the overall, like the quantitative value of information because it will affect this. But it's not going to affect, my argument is, it's not going to affect the scaling of that information with your threshold for how many events you include in the catalog. But it's a very good question. It's messy, and one of the reasons why people use like these multiply Fisher information and similar analysis is because like you can write out equations like this on a board in a real. All right, so in the interest of time, because I do want to get to the microeconomics, I'm not going to show you pictures, but if you go to this paper up here, there are a bunch of beautiful graphs, plots that basically show how it's the fact that you have a heck of a lot more signals at low signal ratios, things that are far away from you, right? Large distances, very quiet sources. You have so many of those that large number of sources overweighs the fact that individually each one of these sources kind of sucks, right? And so the individual precision matrix goes like rho squared. So if I have something that's twice as loud, it's 4 times as informative, right? But if I have something that's twice as loud, it's got to be half the distance to me, and I have a factor of 2 to the 4 fewer, 2 to 16. Right? And so there's going to be 16 times more quiet, noisy things than there is for my one loud thing. And so it's the information from those many, many small things that is driving thing. That's why this depends on growth threshold. Most of your catalogs actually clustered here in a flux line. So, last thing. I've now set this up. Okay, we have an idea of the total information that's available in the catalog. Right, it's that thing way over there. And so now there's a question, if that's how much information I could have if I have n events in a catalog. What is the most cost-effective way to get n events if I'm just observing? And so I'm now going to flex my very ancient undergraduate minor in economics and blow your mind with a one-dimensional minimization problem. So let's say I have some cost analysis. How much money does it cost me to get money, for lack of a better fungible thing? But an overall cost, let's say this is some fixed cost of how much it takes to build the instrument. I then have some operating costs that scales linearly with time. Okay. So if I run the detector for twice as long, I have to pay for twice as much electricity. I have to pay for people's salaries for twice as long. And then I have some analysis cost as a function of the number of events that I have. And so this is like how many MCMC runs I have to do, one for each event. How many like grad students do I have to have? Like how many grad student hours do I have to do the analysis of these events? And so let's assume further that this can be written as ECA n times n. So it's a constant marginal cost, margin analysis cost per thing for that data. Great. Here's a very simple cost problem. Probably too simple to be correct, but hopefully complex enough to not be. So now what do we want to do? We want to minimize this in terms of how long I run my experiments. And then also what's the other knob I can twiddle is like how far deep I go in my catalog, where's my growth threshold, right? So what I want to do is min C over tau and growth threshold. The last piece I need to tell you is how does n scale with growth threshold and tau? Okay. So n, we think about it, it's going to go like some detection rate times how long you run the detector. I run my detector for twice as long, I should see twice as many. And then what is the scaling with the SNR? This comes from the same distance argument I had before. So if you have some road up, So basically, you can think about this, if I go to a lower row threshold, I'm going out to further distances, right? And so if this number is smaller, it's a bigger volume that I'm probing. The volume goes like distance cubed, right? So if I go to half the SNR, that's out to twice the distance. So I will have 8 times as much volume. And so I should have 8 times. So let's now assume that n scales like this, okay? And plug that in. So I can then write C is CF plus C naught tau plus CA n R naught rho over rho threshold cubed tau. That's nice. And so now if we look at this, the minimization, you see here, right? If I just take a derivative with respect to tau, I just get this thing that is equal to 0. And then, or anyway, there's basically that's not a useful thing. But what I can do though is if I take a derivative, yeah, that's it, right? That's exactly what I do. And so with this cost model, you can do the minimization, very straightforward minimization. And so what I get from my notes is that the row threshold that minimizes this should be rho naught. Two R naught ECA n over 1/3. Take a step back, analyze this. What is this telling me? This is some numerical prefactor times the rate at which events happen times the marginal cost per event. This is units of dollars per time, and then, or sorry, this is dollars per time, and this is dollars per event. This is event per time. So the product is dollars per time in how much I'm burning doing my analysis. And I'm comparing that to the dollars per time of just running the operation. And so if it costs a heck of a lot more to just operate the experiment than it does to do your whatever data analysis you're doing, then this ratio, much less than 1. And what that says is compared to your nominal threshold, whatever, you should actually dig deeper into your data. That's the more costly. So don't run your detector as long. Just run it for a shorter period of time and then go real deep into that data. What's the other thing? Well, what if it takes a full PhD to analyze each individual event, right? Then this cost in dollars per event is very large. It's a graduate student for 6 years, right? And then if the rate is not tremendously small, then basically, like if the rate is 1 per day, then I have to enroll and pay for a new graduate student every day. Okay? So in that case, this number can be much bigger than that number. And what this says is, well, I should not look at the quiet stuff, right? I should only look at the very loud stuff, raise that threshold, because it's very expensive to analyze these events. So I might as well just only look at the really loud events that carry a lot of information, and then just run the detector for longer. So I will get few, at my rate at which I will accumulate events is lower, my threshold is higher, but each event carries more juice because it's got a bigger SNR, and then I can throw a graduate student onto that and say, you got 6 years. And so this cost minimization is relatively straightforward. If you plug in numbers at design sensitivity for LIGO, this should be about 1 per day, right? And remember that I gave you candy before you start hissing. The marginal cost per event I've estimated as 10 hours per event, which this is maybe accurate to an order of magnitude, probably not. $30 US per hour in the States. This corresponds to about 60K yearly salary. So this is like postdoc something like that, level salary. But if you also include tuition and overhead and stuff like that, maybe it's a graduate. So this is what I'm saying is that for each event, it would take roughly a graduate student 10 hours of time. And this is how much your funding agency has to pay. And then the other thing you can get is that this is about 10 to the 7 US dollars per year for LIGO. And in my paper, there's a citation to a request to Congress for a budget for LIGO that says 35 million US dollars per year. So bigger than 10 to the 7, 10 million, 35 million, but it's ordered or magnitude. But also they've asked for 35 million every year for the past 5 years, and they're asking the same amount for the future 5 years. What does that tell you? That can't be the actual cost because of inflation. And so the actual cost must be lower than 35. That's my argument. Also, this is a more round number than 3.5. So if you plug these numbers in with current advanced LIGO, the ratio that you get is that rho threshold over rho naught should be 0.28. So this is saying that currently, with advanced LIGO, go deep. Run your detector for however long you're going to run it, and then analyze the crap out of everything you find. That is the most efficient way to do it. If you change this to something like Cosmic Explorer next generation, this is expected to go up by about a factor of 100. If you assume that graduate students don't get cheaper, and you assume that the cost doesn't change that dramatically, like the operating cost. Remember, I'm not worried about the cost of building the detector. I'm worried about the cost. Once I have the detector built, should I run it for longer? So if this is about the same, for Cosmic Explorer, this is a LIGO. For Cosmic Explorer, it's closer to 1.3. So what this says is for Cosmic Explorer, unless we can improve the marginal cost of analysis, or it's just more expensive to run the detector, which hopefully that's not the way you fix the problem, right? So unless we can reduce this number, then it actually makes sense in Cosmic Explorer to not go as deep as we normally can. So our nominal detection threshold here is about 10. And like searches continuously try to get better than this, but it's unlikely that they're going to do like orders of magnitude better. Maybe they'll go to like 9.5 instead of 10. So it's basically around 10. This number is really hard to like make it go down, noise backgrounds. But this is saying that the marginal cost, which is also one of the things that probably has the biggest fuzz on this process, telling you the next generation detectors, yeah, raise your threshold to 14. That's actually a more efficient way to process it and leave data on the floor. And so if you think about in 2015, we had this many detections, right? Now we have several hundred, the catalog is going out. But Cosmic Explorer, which people think might happen in the 2030s, we're now going from like, we have no detection. So the first one's going to be really, really like, let's look at it a lot, to we have so many, whatever, we just shouldn't analyze them because it's actually true. It's not, and it's not that you don't want to, you're not going to analyze them because you don't want to get to something specific. It's just cheaper to run your detector longer. Just wait another day, and then you'll get another 1,000 events or 100 events, something like that. Some fraction of those will be really loud. Look at those. And so, like, it's a change of thinking where you go from sort of a data poor to a data rich situation. And so, anything anyone wants to?
Is trick 3 that it's impossible, like nobody in Congress understands economics, so they won't listen to this and it's too hard to get them to pay for anything?
No, that's trick 4. Actually, trick 4 was that there were 5 tricks. No, trick 3 is the cost model. It's probably too simple to do. Why? This is not linear. Because if the detectors are really old, things start failing a lot. Like this is happening, like the LIGO detectors were built in the 90s. It's been a minute, and so certain things are starting to fail in the detectors, so the upkeep can actually grow for a very long time. But that's the time scale of decades rather than years, so probably okay. The other thing is that I've assumed that this is linear. Almost certainly not. Because of the way that the noise background hits different types events. Some of the events may require a heck of a lot more follow-up. You have to be very careful with voice attraction, or it could even be the case that your sample, your code runs longer for certain classes of events if more difficult to explore. I've assumed that the cost here is entirely driven by labor costs rather than electricity or whatever, like access to computing, things like that. I think that that's probably fair. If you ask like how much does it cost to run an analysis on a GPU for 3 days, 10 hours, right? That is some number of dollars. But typically the labor cost of paying a graduate student to look at plots and interpret this and do the stuff that like ChatGPT may be able to do in 2030, but currently we rely on human expertise with that stuff. That is what I'm arguing is dominating the cost. But that, if it's got some wacky noise stuff, this number could easily inflate by an order of magnitude. In a very complicated way to model, that's why it is. So that is what I wanted to say. I'm a little over time. Thank you for sticking around. I'm happy to take more questions, and people should take more. Thanks.
Over time, so we'll just take the question from Zoom and then we can discuss after this. So one question from Sweden is: do you ever run into situations where fluctuations can be wild and have singularities?
I don't understand the question.
Okay. Sweden, can you hear me?
I was actually wondering, when you're doing the Fisher matrix and you're calculating all the matrix elements, do you ever run into a situation where you need to have fluctuation, calculate fluctuations, and whether they can ever be having singular behavior?
So the Fisher information matrix, where it can be a singular matrix, sucks, but it can be. Depends on how you write down your patterns. It's also the case, very often the case, that it's an ill-conditioned matrix, meaning that the ratio of the biggest to small sagging values is a very big number. That is just difficult to invert numerically. And so there are tricks that you can do to stabilize that numeric inversion calculation. But in general, this is a robust thing. As I said, you can get into a rank deficient matrix. Like if I can only constrain the product of two numbers, but then I try to ask a question about both of those numbers, then I'll get a rank deficient matrix, which they're not linear separable, won't get anything. But it's sort of a different question than
Okay, thank you.
Okay, another question is, I think maybe you already explained, but how many PhDs does the LIGO network cost per day?
I'm not going to touch that. You can take my estimates and run it. I will say that this amount of time per event is almost certainly an underestimate. Like different countries have different wages, effective wages, but over like the cost per event, and also people would argue like, oh, there's economic benefit because we train HGP that enter the workplace. And yes, that's an important discussion. We should have it, but there's some number that can go here. But this number fluctuates wildly, and also the LIGO collaboration has a lot of telecons. Each telecon lasts an hour. They happen every week, and so if people are sitting on a telecon, and you have 50 people on that telecon with 50 person hours to talk about a handful of events and things like that, and so very quickly they can actually build up the total amount of time that is sunk into individual events, even if a lot of the workflow is actually automated, which is people work on this continuously. They've done excellent work to automate everything. I'm not trying to take anything away from that. A lot of the time things just flow and it's great. And this is a big overestimate. Like Aditya, Vijay Kumar here, wrote a different way of expressing the likelihood that speeds things up by a factor of 100 or so. So the analysis is much faster. But sometimes the data doesn't transfer across the internet correctly, and then it's a headache, and then a human has to look at it. And so when that happens, which is with some non-frequency, then the cost, the time. Other questions? Questions now, we'll get two candidates.